My name is Tomas Holderness, and I am the CTO at Address Cloud. And I'm talking to you today about some work that myself and Mark have done on building a serverless geospatial application. And the reason I'm sort of talking today is because we're quite interested in, there's been a step change in the infrastructure that's provided by cloud providers for building applications in the form of serverless infrastructure. And at the same time, in the last decade, there's been some quite significant advances in geospatial technology that have kind of responded to those changes in cloud infrastructure. And so I'm quite interested in the intersection of those two things. What we've got here is we've gone away and built some software which is now an operational product that I'm going to sort of talk to you about today. But having a look at the literature, we can see that whilst a number of studies have gone deep on certain pieces of technology, there's not really been a comprehensive discussion so far that I've seen on serverless infrastructure overall for geographic information systems. So I'm quite interested in that conversation. This paper isn't that. This is just kind of presenting what we've done as a kind of hopefully a sort of first start to that conversation. But for, a little bit of background, and couldn't have had a better introduction to looking at a flood map than the previous presentation. Address Cloud is a company based here in the UK, and we provide geocoding, property intelligence, and risk assessments to underwriters in the insurance sector and also companies in the financial services sector. We have users in the US, in the UK, as I said, in Ireland and in Europe. And the map that you can see on the screen is one of our applications that's showing flood risk for a given location, which we've geocoded against our geocoding service. And then we're showing some property information about that location. And then we're showing this potential chance of flood risk. And we can see that flood risk layer loaded on the map. So our service is all about performing a geocode and then returning information about that location, about that property, and everything we know about that property and its surrounding geographic risk. We're quite busy. We do more than 10 million transactions a month. And it's really, really important to our customers that we are able to perform those geographic queries really quite quickly and to do that consistently, so that as they're asking our service for this kind of information, we're getting it back to them in under a second, and that we're doing that consistently for all of our customers, even as the traffic patterns, as the number of requests that they send to us increases and decreases. And so that's really led us to kind of explore what is termed serverless, which is a fairly unhelpful term that's come out of cloud computing, but serverless can really be thought of as an abstraction of computing resource from an application. And what that means is, as a developer, you need to worry less about a physical or virtual machine upon which your application runs, and you actually take your data and your application code and you hand that to your cloud provider and you say, in request to these certain type of events, please perform this process and return me this information. So you're really sort of externalizing your functional components and not having to worry about those so much, which is brilliant. And also the really other interesting thing about a serverless architecture is that resource is allocated in response to demand. So as you have more data, the cloud provider scales that data storage proportionally. As you have more requests or fewer requests, the compute resource that you're consuming in the cloud increases and decreases as well. So we've kind of developed this as over the last 2 years, and this has now been operational for about a year. This is a high-level architecture diagram of one of our services, the intelligence service, which powered the data and the layers that you saw on the map at the beginning of the presentation. And so kind of high level here, we've got an API endpoints. We're using API Gateway, which is a managed service provided by Amazon Web Services. There are no servers here. There are just endpoints that are in the cloud waiting for connections from our customers or from connections from the application that I showed at the beginning. And then we've got some logic in this service that sits in a function, which is only ever executed in response to incoming requests. And that logic does one of two things. If the location is known to us ahead of time, so if that geocoding process that's happened outside of this service is able to say, yeah, we really know with confidence what this address is, here's a unique identifier, we can look up some information against our cache. I'm going to talk about that cache in more detail in just a moment. For locations that are unknown to us, for example, if an insurer is interested in an arbitrary area, a polygon, say a caravan site or a hospital or a new build set of properties, we've got to go and look up information about the geographic risk that we have against the original data sets that we get from our data partners. We work with a network of data partners from around the world who are feeding us all of these data layers in real time. And we split the processing of those two data layers by their native type. We've got a vector service and a raster service. And the reason for that is that we found that there were some efficiencies to be gained by moving our raster data out, actually outside of a relational database. I'm going to talk about more of that in a second. Now, in conjunction with all of the sort of components that you can see here that are available, have become available from cloud providers in the last, I would say, last 5 years, this kind of architecture has become much more widespread. The geospatial community has also developed some new technologies, and this is not an exhaustive list, but it's 3 things that we've kind of picked to help us enable this architecture. We've got new spatial indexes. We're using the H3 index. I'm going to talk about that in a second. Other sort of similar spatial indexes like Google's S2 are also available. We're using cloud optimized geotiffs, a backwards compatible specification to the geotiff format, which makes it a cloud first format, and files can be accessed directly using HTTP calls. And we've also seen that the adoption of PostGIS is effectively the industry standard for interfacing with spatial data in a relational database. Both Amazon Web Services and Google now offer PostGIS compatible scalable serverless spatial databases. So to talk about that caching layer that I showed, for known locations where we've got address points and property information ahead of time, we can go and look up all of our, run all of our geographic queries in the background, and we can cache that information so that we can serve it super quick to our customers. To do that, we're using H3, which is a hierarchical nested spatial indexing system. It's a very interesting spatial indexing system. It has a number of really interesting properties. I suggest you go and take a look. Not, unfortunately, time today to dive into them. It was developed by Uber to help them map the locations of their vehicles in real time. The reason that we use it is because for any point on the Earth's surface, it provides us with a consistent immutable identifier. So we can say, if we've got a latitude-longitude pair, we can ask our H3 index on the fly, what cell does that latitude-longitude reside within? And what's really interesting is that we can build that, or we can call that spatial index at any point in our application stack. We can run that process on the client, we can run it in a function server side, we can run it in our database. Traditionally, a spatial index would have to exist within a spatial database. And so that kind of frees us from that model and means that we can run that process in the background and then use that unique identifier for our cache.
We've got 3 minutes.
Brilliant, thank you. For our vector service, so for unknown locations where we've got to go and do a point or polygon query against vector layers, and we're backing onto a piece of technology which is called Aurora Serverless for Postgres, and that supports PostGIS. And that's a scalable hot cache. And what AWS have done there is they've taken the data layer of the database and separated it from the compute layer. And then they do some magic effectively, that's how I think of it, where they can replicate that in different places around the world, so that as you make more and more requests to your PostGIS database, that technology scales, and so you can see a kind of a flat curve of response times in response to your queries. Similarly, for the raster service, we took our raster data and we take our big raster files that tend to be at a country kind of scale, when we convert them into cloud optimized geotiffs, we put them in an S3 bucket, which is a type of object store, and then we can query small handfuls of pixels from those files using a piece of software called Rasterio, which is a Python library. And this is actually an infinitely scalable data store. It can store as much data as we can ever create, and we can query that data with a consistent response time, as many queries as we could ever wish to consume. So some kind of performance or some results of that system that we've seen running this over the last year. This is a snapshot I took from our operational monitoring from the last 7 days. The yellow line shows those vector and raster queries. So there's areas that we don't know about. This is the latency of the system. So we'll be able to respond to geographic queries from our customers in under sort of 600 milliseconds on average, which is brilliant. And even the load isn't shown up on this graph, but as the load goes up and down, as people make more insurance queries during the day or in the evening, we're consistently performing those queries. And then the green line shows a response from our cache where we've got known locations ahead of time, and that's working really effectively because we're able to return responses in around about 200 milliseconds to our customers. Last sort of 60 seconds then. it's kind of interesting for us because we developed this as an operational model. We didn't conduct a piece of research to determine whether this was the sort of the best way to do it, but we've tried different things and we've come up with this model. I think that serverless is a viable infrastructure for geospatial application development. It takes away that undifferentiated heavy lifting. I don't need to worry about networking. I don't need to worry about data storage as much. There are some caveats to that. The application is more complex than a traditional monolith, and I need to think about how I can package that code and manage it in the cloud. And there's some really interesting things that are coming up on the horizon. Amazon is supposedly releasing version 2 of its Aurora serverless, which will scale PostGIS databases within milliseconds. PostGIS now supports out-of-database rasters, so we can store our rasters in an object store, but still query them through PostGIS. It's a really interesting hybrid approach that's just come out. And we're also seeing the advent of sort of baked data patterns where people are uploading the infrastructure and the code and the data all up to the cloud in one place to build kind of heavy read-only but very performant applications. So that was me. The best way to sort of contact me at the moment is probably just send me an email. I've written and talked about some of the technologies in today's presentation at our blog, which you can see there. Thanks very much.
We've got a couple of questions coming through. So one from Jeremy is, what leads to the occasional relatively high peaks in the cache response times?
Yeah, I'd have to dig into the data, but I think in that instance, what we're seeing there is when the system cools down. So during the evening, we've got less. Amazon is providing us with less compute capacity because overall we've got fewer queries. If we get quite a big number of queries coming in a short space of time, we'll see an increase in latency as more computing resource is allocated to our environment. So it's kind of an interesting one because with serverless, actually, the more queries you have or the more demand and load you have placed upon your system, the faster it gets, the closer it gets to sort of maximum throughput. As it cools down, as we sort of have this concept of cold and hot, as you have fewer requests, actually your latency tends to increase when you get a subsequent spike. So there's some strategies that we use to try to keep the system fairly warm so that we reduce the spikiness of the graph that you saw.
There's another question here from Nick. So Nick says, really interesting talk. Do you have any useful resources / hints and tips for people who are happy with traditional infrastructure, but looking to move to the stack you outlined?
That's a great question, Nick. I think that there's not one single source of place to go and sort of read about this, which is quite interesting in itself. I think that looking at your application and then working out what your data model is and your data requirements, and then seeing what serverless data stores out there are is probably the way to go on that. So if you think about really, serverless now offers you the ability to store and query data in the cloud. So looking at what you've got, if you're already using PostGIS, for example, then there are PostGIS compatible solutions out there. If you're already doing lots of raster work, then definitely look at cloud optimized GeoTIFFs. If you're looking at document stores, something else that we've used is the Elasticsearch service. So I think it really starts with what your data is and what you want to achieve with that information. But yeah, unfortunately, there's not a good useful resource link yet that I can send you to.
Maybe that's something that could be created, possibly with all the links to resources in the future. There's another question from Jonathan here, who says, how portable is this between the clouds?
I would say it's highly portable. If you think, I think what's really interesting is that we've seen both Amazon and Google independently develop PostGIS compatible interfaces to their big data serverless data stores. So they've both fixed upon PostGIS and PostGIS's functions and interface as a kind of formal API, if you like, into spatial data. So if you've got spatial data in PostGIS, you can take it and you can put it in Google, or you can put it in Amazon. And then our layer that sits on top of that queries that data is very thin. It's really a couple of hundred lines of code at most that's just running SQL queries. And those SQL queries are standard to us. We could run them against any database. And even in some instances, we're not running them against our serverless data stores. We might be just running them locally. So I think you can pick up that code and take it and run it elsewhere. I think the same with the raster stuff. Amazon S3 is sort of the de facto standard for object storage in the cloud now. All of the other cloud providers support the S3 protocol, so you can put your cog in DigitalOcean, you can put it in Azure, you can put it in Amazon. You're not tied to one particular cloud provider.